In this lecture, we will be solving second-order homogeneous differential equation. In order to solve them, first we need to know what is a homogeneous second-order ordinary differential equation. We'll focus on those with constant efficiency. So, the definition says a second-order linear differential equation with constant coefficients is an equation of this form. Let me get my pen working. So it's a, the second order derivative of y with respect to x, plus b times dy dx plus c times y equal to f of x, where these coefficients a, b, and c are all constants. To simplify my future work a little bit, in future I'll write this equation in this form. A y double prime plus b y prime plus c y is equal to f of x. Since it's clear that the dependent variable here is x, so I just use y double prime to represent the second order derivative and y prime to represent the first order derivative. So when is this equation called homogeneous? Well, it all depends on f of x. So there are two stations. When f of x is equal to 0, this equation is said to be homogeneous. If f of x is not equal to 0, of course, it's called non-homogeneous or inhomogeneous. So in this chapter, we'll focus on homogeneous second-order differential equation, which is in this form. So again, I'll rewrite this equation as a y double prime plus b y prime plus c times y equal to 0. Once again, all these a, b, and c are constants. So how do we solve this equation? Well, in fact, in order to solve it, we're going to make a bold guess, or say a clever guess, about what y is. Okay, so we'll guess y is equal to e to the power of lambda x, and to see whether it is a solution for this equation or not. So how can I do that? Well, I can just sub in y equal to e to the power of lambda x to this equation. Well, in order to sub it into the equation, I need to find y prime, which in this case is lambda times e to the power of lambda x, and y double prime, which is lambda squared e to the power of lambda x. When you sub in these values into this equation, we'll get something like this. A y double prime, which is lambda squared e lambda x, plus b times y prime, which is lambda e to the power of lambda x, plus c times y, which is just e to the power of lambda x, is equal to 0. You notice that in these three terms, there's a e to the power of lambda x involved in each and every them. So I can take it out, which give me a lambda squared plus b lambda plus c is equal to 0. Let's observe this equation for a second. Well, it's a product of e to the power of lambda x and a quadratic equation, and this product is equal to 0. So let's pause for a second. Is it possible for e to the power of lambda x to be 0? Well, in fact, it's not, because this is an exponential function. No matter what the value of x is, you'll never ever get 0. So what does it mean? It means from this equation we actually derive a lambda squared plus b lambda plus c is equal to 0. And this is just a quadratic equation. You can solve the value for lambda easily. So this equation actually has a special name when we're dealing with second-order homogeneous differential equation. It's called the characteristic equation, or auxiliary equation. In this module, I'll use this term, characteristic equation. And the essence of solving second-order homogeneous differential equation all lies in this characteristic equation. So how do we solve it? Well, use what we learned from secondary school. We just need to solve this quadratic equation, which I believe all of us already know. So lambda value will be negative b plus or minus root b squared minus 4ac divided by 2a. Okay, so there are two values for lambda now. So one, let me use this notation. So lambda 1